What'll go on in this talk is, so first of all, feel free to interrupt me at any time and interrupt as many times as you want. I probably have about 50 minutes of material, so the idea was that we could chat a lot. The, the goal of this talk is to highlight the role of margins in the analysis of deep networks. And I kind of want to convince a lot of you that this is a very nice way and a very useful way to analyze the behavior of deep networks for classification settings. Did somebody say something? Okay, so yeah, that's the general plan. And to warm up, I'm going to remind all of you about the original appearance of margins in the machine learning community. There wasn't even a machine learning community at that point. This was more than 5 decades ago, 6 decades ago. So the original appearance of margins was the perceptron algorithm and its proof. So here's Rosenblatt's 1950s perceptron. Here's the algorithm. You start at 0. You have a linear predictor. You start at 0. And if your prediction is wrong, if you're on the wrong side of the hyperplane, then you rotate towards the data point, towards it if it has a positive label, opposite if it has a negative label. And if you're right, then you do nothing. So that's the algorithm. And just to show everybody how it runs, so there's the red data, which is negative, positive data is in blue. And you see every time I get a data point, the dot is a little bit, and I just sort of rotate towards it. And here's where the algorithm terminates. So even though this data is just barely linearly separable, right? I mean, that's just such a small amount of linear separability. It still manages to find the linear separator. And so for those of us that have seen this classical proof, it's a very beautiful proof from 1962 due to Novikov. And the proof says, suppose that there is a unit vector linear predictor, which does separate all the data by some positive quantity called the margin gamma. Okay, and the thing I really want to highlight here is that I've looked into this a little bit. This is the first appearance of the margin concept at all. So that for me is already a very nice contribution. So the way the analysis works is you study this potential, the norm of the weight vectors squared, and you do 2 things to it. You expand the square to produce an upper bound, expand the square, use the definition of the update rule, and you get this update. I said expand the square. After you take the square root of both sides, you get this quantity. And to lower bound it, you recursively expand the definition just from the definition, and you get this lower bound that has the margin in it. Then you just drop and you rearrange the equation, and you get that this quantity we had here, which we can interpret as an upper bound of the number of mistakes before time t, is at most 1 over gamma squared. So there are 2 things I want to highlight in this proof. One is that this was the first appearing concept, so that already is pretty amazing. And secondly, we'll touch upon this more, but there is something interesting in this proof, not just that it uses the norm squared potential that we're so used to from convex opt, but the upper bound obtained by expanding the square is a standard regret guarantee, but the lower not. Lower bound is actually quite interesting. Okay, so just to highlight this result and its contribution, so in the decades since then, the margin concept has been applied to many machine learning problems, many statistical problems, and it has a generalization impacts, it has optimization impacts. And for me, philosophically, when I say margin, because of course this is a linear margin, when I say margin, I mean just the most meta version of it is that it's a nice way to capture problem simplicity of classification problems. So yeah, this is the warm up to the talk.
Okay, do you have you seen a formalization of that most general idea there? I mean, because maybe this just reduces at some level down to like a risk bound. I mean, is a risk bound a margin?
So there are times that I've tried to restate it as you can achieve some risk with some predictor of some norm. But if I start from that assumption, I've often run into weird issues because the risk, after all, is an average, but this definition is a minimum, so it's a for all type thing. So no, the most general version, I don't know of a good way to pin it down. And part of what I'm going to talk about today is that what's exciting for me is that I still don't know the right way to write this down for deep networks, and a lot of people are working on it, and that might be a way to address your question. Does that somewhat answer your question?
Yeah, I guess, I mean, maybe one thing you could call a margin would be any statistic of the data and network, which you can use to bound the risk, maybe.
Yeah, again, the only thing that I'll be
Well,
pedantic
that's too
about.
general, that anything that can be used to bound.
Well, in particular, that does not allow you to depend on the distribution. So, you know, I have made a limit there, right? So there's other things I could have potentially wanted to depend on.
Yeah,
but
and I think one key thing is that it really is a for all. So that's one thing that I run into when I try to generalize it to a risk-based definition, which is an average over the data, is I really think it needs to be some sort of minimum.
Okay. Yeah. I mean,
let's come back to it because, like I said, it's open how to write this down correctly for deep networks, or it's open to me. Maybe somebody in the chat knows. Okay, so here's the outline of the talk, and like I said, I plan to have enough material for about until 1, and I will actually skip material so that we have a lot of time to discuss. So I want to go actually back to this perceptron just algorithm. I just want to go back to this and highlight from a puzzle. I was unsatisfied with the perceptron algorithm and its analysis always, and I'm still unsatisfied, and I want to tell you all my dissatisfaction. And we'll come back to that dissatisfaction. Then I want to tell you about a survey of many places in the analysis of deep networks where margins appear. And I call it a biased mini survey because, of course, I'll highlight things that I've been involved in. That's not to say that there isn't, you know, of course, there's infinite amount of beautiful work that I did not do, but, you know, things I talk about, you can ask me about. Then what I want to highlight in section 3 is one very nice way to define the margin for shallow networks, and specifically for the NTK of a shallow network. So this is due to 2 researchers out of Japan, Nitanda and Suzuki, and they have a very nice definition, which then in section 4, I will use to prove a specific generalization, a test error bound on the NTK, or actually just on shallow networks. So let me just be a little bit more precise. In this section is where I'll give the technical meat of today. Everything else will be kind of survey, but 4 is the technical meat. What I'll give there is a test error bound using essentially an elaboration of the perceptron proof, but using this Nitanda and Suzuki margin. And what that means is that the guarantee, in particular the width of the network, the sample complexity, and the number of iterations, the main quantity will be 1 over gamma. There will not be an explicit dependence on the sample size. The baked in dependence is just logarithmic. It doesn't necessarily have to be that the number of parameters exceeds the number of examples. Okay, so that'll be the technical meat. Okay, so let me tell you this little puzzle. So let's go back to the perceptron algorithm and write it in a way that, if like me, you learned convex opt pretty early in your training, is just the most natural way to look at the thing. So let's define a loss function and write perceptron as SGD. So the loss function I'm choosing is just the ReLU. I'm applying the ReLU to the standard thing we use in classification problems that are binary. So here's the inner product of the data and then times the label. Okay, so my loss is the ReLU loss. And indeed, if you just write down SGD on the ReLU loss, so here's the abstract form, we get exactly the perceptron method. So the perceptron method is exactly choosing some subgradient and this usual SGD method. Now, what's interesting to me is that perceptron forces you to choose the one subgradient at 0. Okay, so let me just be a little bit pedantic here. So this loss function is non-differentiable. At 0, the algorithm has to make a choice. What's the subgradient it chooses? And this algorithm forces you, by its definition, its classical 1950s definition, to use the one subgradient. Now, it might sound like I'm talking sentence after sentence about something very technical, but this ends up being, for me, the puzzle of this method. So let's dissect this choice of one, okay? So if you want to say that this, in our classical convex opt setup, is a loss minimization algorithm, and the job is to minimize the average of these losses on data points, then the method should not have chosen the one, and it should not have done anything. It should have chosen the 0 subgradient at 0 and just stayed at the global optimum forever. Okay, so let me say this in another way. If we cast the method as SGD on the ReLU loss, which doesn't change anything, it's exactly the same algorithm. The only detail is what is the exact choice of subgradient at the non-differentiability. So we write this method down, and we know from our convex opt textbooks, this thing should be minimizing, it should be ERM on this. Then the method is weird. It started at the global optimum 0, and it left the global optimum, and then comes back. Okay, and by the way, when I was preparing these slides for fun, I actually implemented this method in PyTorch. By that, I mean, I just wrote down the ReLU loss, and I told PyTorch to just do SGD, and PyTorch happily took the 0 subdifferential and never iterated. It never did anything. Okay, so this for me is the perceptron puzzle. If it's indeed an empirical risk minimization method on this loss, which is I would say the most primitive convex opt perspective on the method, then why is it iterating? Why did it choose the one subgradient? And just for fun, I want to highlight how perverse this is. So what I've depicted here on the right is the same data and the same plot I had earlier where I showed the method just rotating and iterating. And on the left, I'm showing the level sets. So I'm showing the convex level sets of this empirical risk objective. So these convex level sets, it's not depicted perfectly, but here's this is a cone. So this cone here is the 0 sublevel set. That is the set of globally optimal weight vectors. And the method indeed starts these 0, the origin, which is part of this cone. And as you iterate, it leaves the 0 sublevel set and then terminates when it lands back inside of it. Okay, so all I'm trying to say here is, if you apply, if like me, you learned convex opt and you learned the perceptron method within weeks of each other as an undergrad, then it was very confusing to put these together. Why am I leaving the global optimum and coming back? Why didn't I just stay there?
I mean, you could take this perspective, but you could also take the perspective that the objective is not convex. At 0, it actually has the worst case risk. We're just going to forget the fact that it's non-convex, pretend 0 is 0, but then initialize extremely close to 0, and then you'll get like maybe in the limit the same behavior, right? I mean,
well, no, actually. So another funny thing about this, let me give like a meta answer and another answer. So one thing I want to say is that I don't mean to say that my perverse perspective on this is the right perspective. There are many ways to resolve this. One of the standard ones, if you look in Scheichlip-Schwartz's monograph online learning, he uses the classical online tools plus the homogeneity of the ReLU loss to recover the classical Novikov proof from standard regret principles. So the perspective I'm trying to highlight is the one that leads to the shallow network NTK analysis at the end of the talk. Now, to answer your question more specifically, I can't just start near 0 So if I initialize near 0, like where my mouse cursor is now, it's actually possible the method will follow a path that ends up at 0 and then it stops iterating. So it could, if you initialize with a Gaussian, for instance, it's possible that it converges to 0 and then stops. So it really is important that the method starts at 0, exits 0, and then iterates. Okay, everybody in the chat can come up, or everybody in the talk can come up with their own perspective. I'm just saying it is a little bit of a weird method, and it was a lot of fun for me to dissect this method and analyze it in different ways. Okay, are there any other questions at this point? We haven't really gotten to the meat, admittedly. I'm going a little bit too slow. Okay, so now what I want to tell you about is a survey of places where margins have appeared in deep learning apologetically, like I said, mostly with my own work. So first, let me just show you 4 different plots if you haven't come across this before. So this is one of my favorite margin-related plots. What I've drawn here is one data set which is non-linearly separable. So I have red negative data and blue positive data. And I'd fit 3 different SVMs, 3 different regularized SVMs, which are explicit max margin techniques, an RBF SVM, a narrow RBSVM, and a quadratic SVM. So I fit them to this data. I ran the optimization to its core and a good margin separator. So indeed, if we look at these contours, the one labeled 0, if you can see that, is the decision boundary. And indeed, it looks like a good margin. I don't really know what nonlinear margin means, but it looks like there's a good amount of distance on either side. So to everybody that hasn't seen me show this before, I've shown this in talks for about 2 years now. So some of you might know the punchline, but for those of you that haven't thought about this before, it's fun to try to guess where you think the ReLU separator is going to be. And let me just add one thing. This is a 2-layer ReLU network. The number of parameters, I pinned it to about the number of data points. 2-layer ReLU network. I ran SGD with the logistic loss. I ran it a long, long time, and I did not regularize or constrain in any way. Okay, so if you haven't seen this before, maybe just as an exercise, guess what you think happens. And let me tell you that when I ran this, I guessed completely wrong. So I was completely wrong. So I ran it and I got this. It got this very nice, smoothish boundary. We know it's not smooth, of course, but this smoothish boundary that is quite separated from the data. So this for me was actually kind of an epiphany, sort of. I was pretty shocked by this. Okay, so based on this plot, it seems like there might be margins going on. There might be something about where it's putting this boundary, separating it quite well from the data. Okay, so just a little bit of history on margins. So I told you about the Novikov proof. As far as I know, that's the first appearance. The first time that somebody made an algorithm that explicitly maximizes margins. So perceptron method terminates as soon as it gets 0 classification error on the training data. It does not guarantee a good margin. The first explicit margin maximization is due to Vapnik, 1982. That's some version of SVM, like an early, somewhat slightly different stated version of it. And then in 95 is the first generalization bound for using margins. Interesting piece of history is that this is actually a 2-layer network bound. So this is from one of the earlier deep network fads, and then they fell out of favor again, and they came back. So the first generalization bound known using margins was actually for 2-layer networks. And the title of the paper is very suggestive. It says, for valid generalization, the size of the network is more important than this. Sorry, the size of the weights, meaning their norm, is more important than meaning the cardinality of the parameters. So yeah, this paper title is very suggestive. And then the first proof of an implicit regularization. So the Vapnik method was an explicit optimization problem, which says, give me a max margin solution. the first implicit regularization guarantee was due to Rob Shapiro, Freund, Peter Bartlett, and Lee. And they proved that if you just run AdaBoost, so coordinate descent on the exponential loss, if you just run AdaBoost, then you will get a positive margin, and also it will generalize. Okay, so for many people that were trained in the 2000s, like me, this was our first exposure actually to margins. It was for boosting, which was at that time the most popular method. Okay, and so if you want to ask, I will survey, so my own contributions, I will touch on some of these today, not that much though, and if you want to ask me offline, I can tell you, but the 1997 result was with no convergence rates. So it's actually quite easy to prove a convergence rate, and I'll sketch the proof for you. It's actually almost given to you. You almost don't have to do anything. Though I should say that the boosting case is a linear prediction case, so that's why it's easy. Then a lot of you probably know of this paper called Spectrum Normalized Margin Bounds for neural. That paper along the way also gave some evidence that margin maximization is actually happening in deep networks, so I'll mention this briefly. And then a number of people that are in the talk right now, a lot of us had parallel work on maximizing margins for, or finding good solutions for deep linear networks. I won't actually talk about this today. And then what I will do for the final meat of the talk is this perceptron proof showing that ReLU networks get small test error via the perceptron type analysis. Okay, so just to warm up to what the margin should be. Oh, any questions at this point, by the way? Okay, so just to warm up to what could be, I want to do two things in this survey part of the talk. I want to highlight what could be a good notion of margin for deep networks, and also how do people prove that we sometimes can actually maximize the margin with deep networks. So for the linear case, the way it looked was we define this margin. We just take the L2 norm. Here's the definition of the margin. Already for the deep linear case, I would say the problem becomes quite interesting. So let me explain this. So again, we're just warming up. We're trying to guess what it means to find a good margin with a deep network. So for the linear case, it's just a product of matrices. This is what the predictor is. And of course, this product of matrices is just a row vector. So this is just a linear predictor. So we've taken a linear predictor and we've written it with with a lot of layers and a lot of width unnecessary. So what does it mean for a deep network to find the max, or a deep linear network to find a max margin solution? We could just write it as the induced linear predictor. So in other words, the product of all these has unit L2 norm and then satisfies this. But actually, what you can prove is that it finds a much more refined solution. You can prove that if you run gradient descent with logistic loss, the solution it finds, the product of the weight matrices isn't just a max margin predictor, but also the individual matrices themselves have all sorts of nice properties. They become asymptotically rank 1, for instance, and what that means is that the product of the spectral norms of the matrices, or sorry, the 2 norm of the induced linear predictor is the same as the product of Frobenius norms, the product of the spectral norms. So the solution has a lot of structure. So let me just be a little bit more clear what I'm trying to say here. How do we characterize the margin maximizing solution for a deep linear network? It turns out you can write down something much nicer than just that it's the solution which has the product of the weight matrices having L2 norm 1 and a good margin. If you write down the full description, it also has all these other properties.
And it's not that they're all diverging to infinity,
sorry,
are they? It's not that they're all diverging to infinity, is it? Or
so yeah, let me just say a little bit more then. So in the this is something I didn't mention yet. So if we're in the linear classification setting, and we use something like the logistic or the exponential loss, and the data is linearly separable, the solution is off at infinity. So in order to get zero training error, you actually have to push the product of these weight matrices out to infinity. But here's the interesting thing. So about 2 years ago, so we know that the product of the matrices has to go to infinity. About 2 years ago, Jason and I think Simon, at least one of them were in the talk earlier. So they proved that for positive homogeneous networks, the norms of the layers become, or they stay roughly the same. So if you run gradient descent for a really, really long time, they basically have the same norms. And what this means for our case is actually that all the weight matrices go to infinity. So all of them go to infinity, and if you then normalize them by their norms, you look at them as unit Frobenius norm matrices, then they have all sorts of nice properties.
Matus, a quick
Yeah.
question. Are these results kind of like the Srebro group kind of results, or do you actually analyze the trajectory from initialization?
Oh, I see. Yes, that's a good question. So, and then there's also your work with Nadav Cohen and I think Wei and a couple other people. So yes, so I will get this later in the, maybe in 5 slides. There are a number of results that the theorem statement is suppose your iterates converge and suppose the gradients converge and maybe also suppose you get zero training error, then the solution you find has some properties. Most of Nati's results are like that. His linear convolutional network results are like that. Not all of Nati's results are like that. For the deep linear one, they are. This theorem is not like that. This theorem, let me be a little precise. So this theorem, it's from a paper that Zoe G and I did. It was titled Gradient Descent Aligns the Layers of Deep Linear Networks. It starts from essentially random initialization. So it just starts from a low risk point. It says, suppose that your initial risk is below the risk of the zero predictor. Then all of these nice properties happen. So Sanjeev, going back to your question, the paper you did with Nadav Cohen, for instance, it assumes this balanced initialization. We don't assume that, but on the other hand, your paper has a linear convergence rate and we do not produce any convergence rate.
Wait, so this works from any random initialization?
Yeah, it does work from random initialization. But I would say, so you guys have another assumption, but on the other hand, you guys gave a rate. We did not give a rate.
No. So look at the newer paper. You're assuming small random, right?
Sorry, say it again.
Small random initialization.
Let me just be a little bit more clear. We actually allow deterministic initialization. The only condition it needs to satisfy is that your initial point has risk which isn't too bad.
Okay, got it.
Yeah. So, but again, we didn't prove a rate, so it's kind of apples and oranges.
Can I ask something?
Yeah, of course.
Okay, sorry. This is my first time using Zoom, so I'm not sure exactly, but I think it's working. I didn't quite understand your theorem because aren't these products all going to infinity? So what does it mean that they're all equal? You're just saying they all go to infinity?
Yes. Yeah, let me say a couple things here. So this was my mistake. I did not state this theorem precisely. I mean, it's stated precisely in the paper. I tried to state it in a way to sort of surprise people, but it ended up just being too vague. So I apologize for that. Indeed, all these weight matrices go to infinity. So what I should have written here was, well, one way to write it is that if I normalize asymptotically, these become the same, but they do go to infinity. So one thing I can prove is that if I take the ratios, so if I take this divided by this, as t goes to infinity, then that goes to 1.
Thank you.
Yeah, that was my mistake. Let me actually skip the next slide because many of you are extremely familiar with this and it's not something I'm going to talk about. I briefly just pointed out another way to define margin. If you looked at that spectrum normalized paper, we had this convoluted way to define the margin. And I don't want to talk about generalization today, so I'll just skip this. Let me just say two things before getting to the perceptron type analysis. So I just want to comment on how you actually prove margin maximization. And this, for me at least, this also goes back to Sanjeev's question about what are our initial conditions on that theorem. So one very nice way to prove margin maximization is to recall, of course, that the margin, which is defined as a minimum over all of these prediction outputs. So of course, we're all familiar with the fact that the log sum exp approximates the max or approximates the minimum, the negative log sum exp. And if we're using the exponential loss, so sorry, let me say this in a slightly more detailed way. So in all the settings I'm talking about today, I use the logistic loss. And the logistic loss, after you run for a while, starts looking like the exponential loss. Okay, so we're effectively minimizing the exponential loss. And if I just put a log in front of it, I've got log sum exp, it starts looking like the definition of margin. Okay, so if you just write down our margin at time t, which is the minimum over the individual data point margins divided by the norm, if I just write down the definition of margin, and then I just note that this is greater than or equal to the log sum exp, and then introduce 1 over n, right? I mean, I'm not even skipping steps here. So the margin is lower bounded by the log of 1 over the minus n divided by this norm. Okay, so I can lower bound my margin by an expression involving the risk. So this is pretty great because this is what we're minimizing in the algorithm anyway. So if the algorithm minimizes risk and keeps small weighters, we're proving good margins. Okay, and I'll only sketch it very briefly, but I mentioned that in 2013, I proved margin maximization for coordinate center boosting methods, and this is basically the proof. There's really nothing to do. So you start from this right-hand side over here. Using classical results on boosting, you don't even need to prove a new lemma. You just plugging in essentially the iteration guarantee for boosting. You get that this log 1 over r looks like the margin times the norm over the weight vector. So basically for free, you prove you are 1 over log t essentially close to a good margin. Okay, and so the only thing I want to say here is that this convergence rate is very slow to highlight. The convergence to a good margin solution is 1 over log t, which is just horrifically slow. So all the main results I'm presenting today will be with Zoe G, who's in the participant list, and he'll probably comment at some point. One thing we discuss a lot when we're working on these problems is that the convergence to the margin solution is so slow, it's effectively asymptotic, that is this even a good notion? Is this even a good thing we want to prove? So if you've been wondering how slowly you converge to this and if it makes it a practical quantity, good question. It's a very useful thing to wonder about. Okay, so let me just say a little bit more about these proof techniques. So again, I'm just kind of surveying for you some places, some ways to prove margin maximization. So this idea of using log 1 over the risk has appeared many times, and I think it's been discovered in parallel. So Kaifeng Liu, who was supposed to be Sanjeev's student this year, but he's still in China for various reasons, unfortunately. So he has an ICLR 2020 paper that says that if you run gradient descent on a homogeneous network, so let's say a multilayer ReLU network, and what he calls the smooth margin, which is just this log 1 over risk, is actually non-decreasing. Yes, that was not on my end, but that was a very welcome interruption, so thank you. That was much cuter than I sound. Okay, so yeah, so this quantity, this log 1 over r, it's actually non-decreasing if you run gradient flow or gradient descent on a homogeneous network, and this is due to Kaifeng Liu and Jian Li. And the proof has many interesting steps. It's a very nice proof. And one of the other things it proves is that if you run gradient descent and you look at the trajectory, its limit points are KKT points of a certain, another way to write down the margin maximization problem. So I'm highlighting this proof for a number of reasons, but one is that it kind of centrally uses this log 1 over r concept, or this quantity or potential, but it brings up another essential quantity from the study of margins mathematically, which are these KKT points of this margin. Let me also point out that there's a very recent paper from Chizat and Bach. This is not one of the ones people are that familiar with. This one's from 2 months ago. It just got posted. I guess it's an ICML submission. And they use the log 1 over the risk in a different way, and it's very fascinating. They essentially rescale time. They treat the gradient flow as being not on dr dw, but on d log r dw. So this is amazing. So again, the way that they introduce log or log r is by rescaling time. They don't treat it as a potential function, they rescale time with it. And they prove that, sort of like Sanjeev's question earlier, they prove that if you assume, kind of like many of Nati's papers, if you assume that the iterates converge in direction, and that the loss vector or the gradient of the loss converges in direction, then you actually find a max margin solution. Okay, so these are 2 recent works. This is Kaifeng's paper, is an ICLR 2020 paper. The Chizat paper just appeared on arXiv 2 months ago. These are 2 very nice works. I think these are the kind of the most current, most recent margin maximization results for deep networks. Okay, so, and let me just say briefly that, so one concept that people use in these proofs is this log 1 over r potential. Another one is to just write down the classical SVM style margin definition. So here's if you make f just be a linear predictor, this is the SVM margin. You look at this and you study the KKT points of this optimization problem. I say KKT points because f, if it's not a linear predictor, this is not a convex problem anymore. So now we just look at these KKT points, these potentially local optima. And yeah, this is another way to do the analysis. Like Sanjeev was pointing out, often it means that the results are very asymptotic, but it can also be used to prove rates. And many of the proofs now are, I'd say, hybrids. So there's kind of a log 1 over r and a KKT story in both of these papers. So for those of you that want to work in this field, I would say that these 2 techniques are very promising, these 2 analysis tools. Okay, any questions at this point? Okay, so what I'll do now is I'll tell you about this margin definition for the NTK due to Natanda and Suzuki. And then in part 4, I'll tell you about how to use that with the classical perceptron proof to show that gradient descent on shallow ReLU networks gets epsilon test error with a very small width and sample complexity. Okay, so many of the people here know this way better than I do, so I will just kind of try to be quite minimal here and also give a perspective that I think helps develop the margin assumption. Okay, so a lot of you know the NTK. The original contributors, kind of it all happened in parallel, but all of these papers have very nice ideas. So the idea is we linearize the predictor, and the key idea, I'd say, of the NTK is not to linearize around 0, which has all sorts of issues you linearize around the initialization. And in this talk, when I say the NTK setting, what I mean by setting is that the features you get by linearizing around the origin do not change much. Sorry, around the initialization. So when I say NTK setting, I mean we haven't run too many gradient descent steps, and our features still match those at initialization. Also say that because in this talk I'm always using the logistic or the exponential loss, because that means the solutions are f in infinity, and that means that we are actually changing a lot of activations, and we're always exiting the NTK. Okay. So let's try to make a version of the margin definition, but for the NTK. So what I've written here, the first idea, I would say this is essentially a direct translation of our earlier linear margin. I'm saying there exists some positive number gamma and a matrix now, a weight matrix U, that has unit Frobenius norm such that for all data points, yi, so as before, times, now earlier we just had U transpose X, but instead we have matrix interproducted with the features that the NTK works with at initialization. Okay, say that this is just a direct translation of the standard linear margin, but we've replaced the data with the features that the Rayleigh network works with at initialization. Okay, so this definition is actually not good enough for us. It has a couple issues. And the two I would like to highlight is that first, it seems like a bad idea to use the Frobenius norm. So the Frobenius norm, it can have some, so your Frobenius norm can be 1, and you can be putting all of that norm on one row of the matrix, or just 2 rows or something. And what that means is you might actually be exiting the NTK. So saying it another way, if we make the condition that the Frobenius norm is 1, then this linear predictor might not be related to what the ReLU network with weights W0 plus U is actually doing. So our goal, of course, is to analyze not the NTK, but our goal is to analyze a ReLU network. And if this definition causes a lot of the activations to change, then it's not useful to analyze ReLU networks. So the way we'll fix that is we'll require that instead of being Frobenius norm, we'll make it be the to infinity norm, and we'll make this. We'll use some rescaling so that it effectively it'll be like 1 over root m, and that'll guarantee that if we look at W0 plus U and plug back into the ReLU network, few of the activations have changed. Okay, so that's one issue. Another issue, and for this one, I'm even kind of more fascinated by how by Tandon Suzuki's idea and their construction. The other issue is that this is a random variable. So this margin assumption is no longer a property of the data or the distribution. It depends on this random matrix W0, right? We can't state a theorem anymore that says it's not a data assumption. It depends on the weights. So the idea is to replace this with an expectation. Okay, so if we, let me explain this a little bit more slowly, or let's just go from this equation down here. So here's what we have up there. It's this reparameterization, or this U interproducted with the features at initialization. And now I'm writing it out in a special way. So I took the rows of the weight matrix W, or W0, and I transported them. What I mean by this is I'm picking some function T that takes all the rows and it kind of moves them in the way they want to go. So the margin assumption is actually going to be that there exists some function T, or if I take the features corresponding to X and W1 through X and WM, and I kind of nudge them in the right direction, then I get a good predictor. It'll be more clear on the next slide, sorry. Okay, so U is defined to be all these transports, which I can just write down as a sum over m different, now vector-wise, inner products. And if I write this as an expectation, I look at the features I get with this random W. Oh, sorry, this J should not be here. My apologies. So W is a random variable I'm taking expectation over. It's a Gaussian random vector. So I have the feature I get with this W, and I inner product it with this transport, which says, what is the linear predictor I want to use with this random feature? And yeah, so here is what I'm going to plug in up here. This is going to be an infinite width. It's an infinite width linear margin assumption. Okay, so let me just put it up and then perhaps, oh yeah, sorry.
So
go ahead, sorry.
You started talking about this transport map after raising the the apparent problem of how do I say a theorem which has a random variable in it. I mean, there's a traditional way to do this is to say that this logical expression holds with high probability, right? So that would be one possibility. And now and it
sure,
seems
that's
like
fair, yeah.
And here it seems like they're going for maybe instead of controlling kind of the tail of this logical formula holding, they want to make a statement about a mean or something like that. Is there a reason why maybe a high probability these two existential doubly existentially quantified formula holds, why that isn't the right way to proceed?
So I think another key thing to highlight here is the infinite width perspective on deep networks, or neural networks, which I guess I haven't been highlighting in this talk, so that's my mistake. So this version is also nice because if we take the perspective that, I guess a lot of people have now, which is that the infinite width version of the network is kind of its pure form, then it's very nice. Now we're stating the assumption on the infinite width version, and we're treating the finite width versions as subsamplings of this. And in particular, what you were saying earlier about getting a high probability guarantee, indeed, when we prove our final theorem, it'll be with high probability, but it'll be not only over the data, it'll also be over the random weight matrix. And that random weight matrix will have to concentrate around the behavior of this one, of this infinite width object.
Okay, thanks.
Okay, so just a couple comments on this assumption, and I'll pause here for more questions, because for me this is one of the most exciting things I want to highlight for all of you is actually this assumption. So again, the definition now is there exists a margin gamma greater than 0 and a transport. So think about this as a linear predictor to assign to the corresponding features, such that each individual element, I always transport to something that has unit L2 norm. So this for me is like the to infinity norm on that whole induced thing. Okay, and then I state two versions of it. One is the sample version. So for all xi, y in your data set, this expectation or this network gets margin at least gamma, this infinite with NTK, sorry. Infinite with NTK gets margin at least gamma. And there's a distributional version of it, which is that almost surely over the XY pairs in my prediction problem, the infinite with NTK gets a margin gamma. Let me just say that I'm introducing both versions here because in order to prove our strongest theorems, where the network's width does not depend on n in any way, it's most clear if we use this distributional version. And that way it's clear that there's no n baked into gamma because n doesn't mean anything, it's over the distribution. Okay, so just a few comments about this definition. Just to sanity check that it's a good and interesting definition. So one, if the data is linearly separable, we would hope that this margin is actually related to the linear separability margin. And that's indeed true. If the data is gamma 0 linearly separable, using the same linear separability definition from earlier, then this margin is gamma over 2. And that for me is extremely exciting, because that's telling me that if you give me linearly separable data and you plug it into a shallow ReLU network, then if this margin assumption is actually meaningful, then the dynamics of the network on this linearly separable data should actually behave like the linear separator. So I'll make this more concrete later, but when we prove the theorem, everything's going to depend on essentially if it's the linearly separable data on the linear margin, and the convergence rate, the width, and all of these things. So that's pretty exciting sanity check for me. Another thing is that it's of course natural to ask what data is linearly separable. So linear separability is a very strong assumption. What about this assumption? This actually really isn't an assumption in the sense that the NTK itself is a universal approximator. It can fit any continuous function. And so as long as I have clean data, so I never have the case that I have a single xi and two different yi's for it, then I can always find this t. So this isn't really an assumption, it's just kind of a characterization. Many people care about distinguishing random and true labels, and it's very nice. If you just start with some data and you randomize the labels, then this margin becomes 1 over root n. And let me tell you why that means something interesting. So for perceptron, the number of iterations was 1 over gamma squared. And if gamma is 1 over root n, then 1 over gamma squared is n. And what that means is perceptron, the mistake bound is vacuous. It's saying we made a mistake every time. And that's what we expect. If we have random data, we should not be doing anything useful.
What do you think about this, the population assumption in, on, say, vision data sets where we might believe that there is indeed a perfect classifier?
Okay, so another very good question is, what actually is the gamma for regular data, and does it actually enter the regime that the theorems start to be non-vacuous? Do we, if I do actually get a sample complexity of 1 over gamma squared, I will in 20 minutes, I will, but do we actually get a bound that's less than 1? So I did not run these experiments. Zue, who's was Zue and I, he's one of the participants. He ran this on at least MNIST, and it was ballpark to be a good bound. CFAR, I can't tell you. But to say more about your question, I personally would be really fascinated in writing down some legitimate definitions of multi-layer margins, or even like convolution layer margins, and all these things, and just calculating it for a bunch of different data sets and seeing if this approach has a hope of getting a good, good analysis. I don't know, Zue, if you're there, do you want to say anything? Do you want to add anything?
Oh, yeah. Yeah, I tried some experiment, at least I tried on MNIST, and I think like the test error, if you use the pure NTK, is almost as good as like the test error for a normal network. So I guess, it is, because I did that experiment, I think I'm okay with making this assumption, like some assumption on the separability of the features induced by the NTK.
And do you remember what it was for that experiment? Do you know if it was like 0.01, no?
Oh, you mean the margin? Okay, yeah. The margin is 0.0, yeah, 0.02 or something like that.
So yeah, for MNIST, if I'm not doing my math wrong, that'll give, just from the 1 over, or the 1 over gamma squared times 1 over root n, I think that'll give like error 10% or something between 1 and 10%, Dan. So it's bad in the sense that for MNIST, we know that we should just be getting some ridiculum, but at least it's, you know, kind of ballparky, or I don't know, at least it's not 1.
All right, I think that's in the zoo of bounds that are out there. 10% is excellent. So I'd be curious to see those calculations.
But for CFAR, I'd be a little bit scared, yeah. And for CFAR, yeah, I'd be pretty scared.
Yeah, CFAR is another animal altogether.
Okay, so I promised I would be much faster. I was not. Let me try to be efficient so that we have a lot of time for a lot of discussion. What I'm going to do here is, most of my slides actually sketch the proof. I will just do this at a very, I'll do this at a very high level to sort of get your interest and convince you that this can work. I should also say this proof is very, very short. It's not much. It's basically the perceptron proof plus some of the standard ideas from NTK proofs. And so if it interests you, you can check it pretty quickly. But I'll kind of go quickly to the theorem so that we can discuss a lot. Okay, so let me just tell you the setup. I'll do this carefully. By the way, if there's a black box in the screen, it's saying my connection's unstable. Sorry for that. Okay, so the setup is shallow ReLU network. I'm only training the inner weights WJ. The AJs I fix initially at -1 +1. And the predictor, I rescale the predictor by 1 over root m. Many of the NTK papers do that. Because of homogeneity, this is equivalent to having a 1 over m variance on these WJs. So that's standard. Also, by putting the 1 over root m in the predictor, I'm rescaling my step size in this gradient descent proof by 1 over root m. Okay, but I mean, the main thing you should take away is this should be completely standard. And if you think I'm cheating anywhere, you should call me out, because we really tried hard. And so yeah, I should say that this part of the talk is joint work with Zue G, who just spoke, and the proof is 99% his effort. Okay, so we use the standard logistic loss, cross entropy for 2 labels, if you will. And we analyze both gradient descent and stochastic gradient descent. Usual ones, usual definition. It looks like the step size is 1, but it's actually 1 over root m, because we have a 1 over root m factor in the predictor. Okay, so this should look very standard.
So this is like a one hidden layer network?
Yes, it's a one hidden layer, did I just say hair? So it's a one hidden layer network.
And you're fixing all of this.
So it appears in many papers. Yes, so I like this setting personally because it's, I would say, the simplest non-convex neural net training problem. So we're training the W's, which are inside the ReLUs, so it's a non-convex training problem. Let me just make one random technical note. For those of you that noticed, I mentioned the Chazot-Bach margin maximization paper earlier. That paper focuses on the 2 homogeneous case, which you can kind of think of as training the outer layer too. It turns out it's actually a really good idea to train both layers. Yeah, let me just throw that technical comment out there. Okay, so let me just say quickly how the proof works. In the perceptron convergence proof, if we treat it as SGD on ReLU loss, like I mentioned earlier, then the quantity, which is the number of mistakes up to time t, if we use the logistic loss, not the ReLU loss, this mistakes up to time t, it becomes this quantity, which is the average of the derivatives of the losses on the examples up to time t. So this is a pretty interesting quantity. It's not just the sum of the gradients, because the gradients have this chain rule term here where I have grad of f blah blah. This is not the average of the gradients. This is it's based on the cumulative derivatives of the losses. And I claim that this is identical to the quantity used in the perceptron convergence proof after you call it gradient descent on the logistic on the value loss. So given this perspective, I claim that we can now just rerun the perceptron proof and get something interesting. Just rewriting it for the logistic loss and for this shallow network. Okay, so I will just sketch this so that I can get to the theorem and so we can discuss a lot, especially since there are a lot of people in this talk that have a lot of parallel and prior work. So when we proved the perceptron convergence guarantee, we took the potential function Wt squared, we upper bounded it and we lower bounded it. We upper bounded it by expanding the square and using standard regret techniques. And if you do that here, it works in the sense that you get a bound that looks like what we used for perceptron, or a standard regret bound with a little caveat. So let me explain this. So I claim you just get this by expanding the square. Left-hand side is distance from, let me state this theorem more precisely. So the way I'm stating this regret bound is I pick some comparator vector z, so some good solution z. So if I look at Wt, the iterated time t, minus this comparator z for medium squared plus of the risks up to time t, then that is thus equal to the distance at initialization from z plus, now this is where it gets interesting. This isn't the risk of this comparator, this good solution z, it's the risk of z had I used the initial NTK features. So that's what's, or sorry, if I had used the NTK features at time I. So that's what's going on here. So let me, the proof is basically the standard regret bound proof, but of course the standard regret bound proof assumes a convex potential. We don't have a convex potential because the neural net predictor is a non-convex function, but it's a homogeneous function. And if you do some algebra using homogeneity, it's really just maybe, it's 2 extra lines, then you can prove this very interesting bound, which replaces the regret or the risk at time I with the risk using the NTK features at time I. And of course, if we can guarantee in the proof that we stay close to initialization, then this will be like the using the NTK features. Okay, so I'll just say briefly that if we, let me just remember what the last slide, oh yeah. So for Z, what we should use is the initialization plus this matrix Z, this matrix U we get from the Nintendo-Suzuki assumption. Why do we use that? If you plug that in here, then it cancels with the W0, so we just get some small thing inside the Frobenius norm. And here, because of just the definition of the assumption, we can prove that the risk is small. So with this choice, we can make this entire right-hand side small. And a key part of the proof is also lower bounding this norm quantity, just like you do in the perceptron proof. And again, we can use the definition of, we can use the definition of U. So let me just say there are 3 ingredients to this proof. One is a regret upper bound, mimicking the perceptron regret upper bound, which is adaptive homogeneity. Then the second key ingredient is using the Nintendo-Suzuki margin definition, which allows us to essentially get the same thing like the perceptron bound. The third ingredient is the NTK setting. So in order for all of this to stick, so in other words, in order for the features at time t to look like the features at time 0, we stay close to initialization. And the proof looks like a standard NTK proof in the sense that we assume that this is, I would say, in the Chazat-Bach lazy training papers where they presented it in the first way that, or this is one of the first place that I learned of it this way. So you assume that you stay close to initialization and you study what happens close to initialization, and then you prove that actually you stayed in near your initialization for a very long time. Okay, so those are the three ingredients. Before I give the theorem, let me just say one more thing about the proof, which is how we prove generalization. So this for me is fascinating, partially because I wanted, okay, just to be clear, this proves low training error, what I just said. But then to prove low testing error, we apply a generalization bound. The interesting thing for me is I wanted to use the spectrally normalized bound, and Zue found a different way to prove generalization that got a better bound. So to prove generalization, he did not apply generalization or uniform convergence to the logistic loss or to the 0,1 loss. He applied it to this function Q. Q was the average of the derivatives. It was our analog to that key quantity in the perceptron proof. So Zue applied uniform deviation to Q and then used the fact that the derivative of the logistic loss, which is the sigmoid after all, is at most 2 times the 0,1 loss. So yeah, so using this, you can get a very strong generalization bound. And for stochastic gradient descent, it's similar. Again, you construct a martingale using this Q function, and you get a bound. So here's the theorem. So here's the theorem you get. So for gradient descent and stochastic gradient descent, so for gradient descent, so suppose the width m and the samples n satisfy the following inequality. So the width m is at least 1 over gamma to the 8th, where gamma is that infinite width, the Suzuki NTK separation assumption. So the width is 1 over gamma to the 8th times a bunch of log factors, log in n, log in 1 over delta, log in 1 over epsilon. Okay, that's the width. And it really is just less greater than or equal to that. It can be infinity, it doesn't blow up, or it can be this times 10 to the 1,000. That 10 to the 1,000 will not enter in the test error bound. Then the sample size is 1 over epsilon squared times gamma to the 4th times log n, log 1 over delta, log 1 epsilon. And the number of iterations we have to run is roughly 1 over epsilon gamma squared. So the theorem is that if your sample size, if your width, your sample size, and your number of iterations of gradient descent satisfy those 3 inequalities, then probability 1 minus delta over the data and over the initialization, your test misclassification error is less than epsilon. Oh, and I should say that it's not for WT, it's for the WI that has the smallest risk in that first T iterations. Okay, and then for SGD, the theorem is similar, but it's a little bit better. So the size is the same as the number of iterations, and it's tighter. It's just 1 over epsilon gamma squared. So n is no longer epsilon squared gamma to the 4th, it's epsilon gamma squared. And the test error is the online stochastic error. So if it's an ERM problem, it's equivalent to test error, but it's the test error you get by sampling data points at random and then averaging across all the prediction rounds. So let me just make some remarks, but then it's actually fine. I mean, I just have thank you slides. So I think I'll just end on this slide, and then we still have technically 12, 13 minutes to discuss. So let me just make a few remarks. So one of the fascinating things, and this is actually something that happened in the ICLR reviews. So the ICLR reviewers were concerned. One of them said that gamma looks like it could always just be order n, or sorry, 1 over n. And so these bounds are actually, either the same or worse than all prior work. So Zue worked hard, and he proved some interesting lower bounds. So if you consider the noisy 2XOR data, so noisy 2XOR was highlighted by Colin Wei and Tongyi Ma in a paper called Regularization Matters. So it's a noisy parity problem, basically. And for that problem, you can prove that in order to get better than some constant test error, you actually need the width to be at least 1 over root the margin. For this problem, the margin is effectively 1 over d. And you need the sample complexity to be 1 over gamma squared. So the fascinating thing, this is the second line, is that our upper bound for SGD actually matches in terms of sample complexity this lower bound. And I should say that this lower bound I'm stating for n, the sample size, it's the NTK lower bound. So it's the lower bound for a kernel method, essentially. Okay, and then the main contrast between this theorem and, let's say, this fine-grained analysis paper by Sanjeev and Wei and others that are mostly in this talk, the main thing is that we don't bake in a dependence on n1 over epsilon or 1 over delta. It's log in those. Of course, there are cases like random data where gamma can be very bad. It can depend directly on n. But also cases like this noisy 2XOR where it's very good, or the linear separable data. Okay, so I'll stop there and leave the floor for questions.
Hey, Matus? Matus?
Yeah.
Can I add something for the lower bounds?
Yeah, I'm listening.
Okay, sure. Yeah.
Oh yeah, of course.
Okay, so so this with lower bound m, at least 1 over square root of gamma, it's actually a lower bound for an NTK analysis, which means that if the width is not is smaller than 1 over square root gamma, then you cannot. Then the initial features induced by the NTK are non-separable, so you cannot use NTK style analysis to show a convergence result. But I mean, we're not saying that a neural network can solve the problem, because maybe gradient descent on neural network can eventually exit the NTK phase, and maybe it can even like break the initial non-separability. So that's an interesting open problem. And also for this sample complexity lower bound. So in the prior paper by Wei Li Liuma, they proved sample complexity lower bound of d squared for noisy 2XOR. And in our paper, we calculate the margin for noisy 2XOR is 1 over d, which is and it's 1 over d, and so I mean, so which means a 1 over gamma square sample complexity lower bound. And note that we also, I mean, just on the same slide, we showed a sample complexity upper bound for stochastic gradient descent of 1 over gamma square. So actually that matches the sample complexity lower bound. So which means that it's tight. I mean, now we have a tight sample complexity analysis for noisy 2XOR and for infinite width NTK. I mean, all these lower bounds are actually for NTK. I mean, if you indeed use the NTK style analysis, and perhaps you can get a better bound if you use neural network, but you may need a different analysis.
Yeah, let me also add that based on what Zoe just said, I realized, and I extremely apologize, I've left 2 authors off. I got confused between 2 papers with Colin Wei and Tongyu Ma. So the paper I've been mentioning as just Wei and Ma, it was actually with Jason Lee and with Cheng Lu. So I'm extremely sorry for having mistaken that reference. I'll fix the slides. So are there any questions or comments?
Can I ask a really naive question?
The talk was very naive in parts, so of course it's part of the course.
Can you give like a geometric idea of what your method is based on? Like have a relatively narrow network, and you have a data set that has some margin. Are you using some sort of quasi-convexity of the loss function? Are you using that you're not going very far? What are you?
Oh, so it, okay, so if one of the questions was, what is the geometric interpretation of what's going on here? I would say there are two places to look for geometric interpretation. One is in the Nintendo-Suzuki assumption, and it's actually very hard to, or I find it very difficult to actually prove, if you just give me some data with some structure, what is the T and what is the gamma? It can be kind of difficult to prove, but actually, let's say for some data, it's very nice and geometric. So for instance, for linearly separable data, what you do is kind of funny. You create two copies of the linear separator. You put one that you make one just be a duplicate of the regular linear separator, and then you have a second one which points in the negative direction. That's because the ReLU kills off negative stuff. So I would say that here there's some geometric intuition. Where that geometric intuition appears in the proof, I'm not sure, because this is just opaque. Kind of on the second half of your question, and another place where geometry occurs, I would say is here. So absolutely in the proof, I went too quickly on this slide, and I kind of was just completely unclear in what I was saying. But just like all the other NTK proofs, this proof requires you to stay close to initialization throughout. That's absolutely going on. And this regret inequality, which has both the risk and the distance to something on both sides of the inequality, we use this to simultaneously control the distance and the risk. So that comes in there. The other things you said, quasi-convexity, things like that, that's not used anywhere here. The only structural property we use in it is that we use the fact that the loss function itself is convex. I mean, in its input, the problem is not convex, but the loss is convex, and the predictor is positive homogeneous. We use that heavily.
So should I have in mind the picture that for the like hyperparameters that you've chosen, wherever I initialize, I'm pretty close to a global minimum?
Well, yes and no. The reason I'm kind of becoming very uncomfortable is, what does pretty close mean? So the norm we're using here usually is the 2 infinity norm over the weight matrices. But that for me is a really hard norm to visualize. So let me say what I mean. The NTK, one perspective on what it's doing is by making the width very large. I'm basically just like duplicating a bunch of rows. I can take a good solution and just duplicate a bunch of rows. So in the 2 infinity norm, I'm staying close to initialization, but in Frobenius norm, I'm still a constant away from the initialization. So I'd say that the choice of norms sort of complicates the geometric picture. I mean, does anybody else want to answer this question? Because I see, I see like Wei in the chat. Jason was in the chat at some point, so, or Jason is here. I mean, do any of you want to? Jason or Wei, do you want to, or Sanjeev, do you want to chime in on this question? The closeness and the.
I think
I'd
I can
be happy to hear your comment there. Oh yeah, sure, go ahead.
Yeah, I think, so indeed, I mean, it depends on which norm we use. If we use a 2 infinity norm, in other words, if we use the change in each row of the weight matrix, then it could be indeed small. And a small 2 infinity norm can ensure that the features of the NTK doesn't change too much. But on the other hand, to have a small risk, actually, I feel that we should not only look at the change in each row, but we should look at maybe the Frobenius norm, or in other words, like this, the sum of the changes. I mean, the thing happening here is that the Frobenius norm can be pretty large. It could have size log 1 over epsilon, which is basically what you need for an epsilon error. But on the other hand, because we have multiple hidden units, then the Frobenius norm the to infinity norm is basically the Frobenius norm divided by square root of m, divided by square root of m, which can be small and which can ensure that the features do not change too much. I think that's our idea.
Thank you.
Any other comments or questions?
I'm curious what you, do you know anything about lower bound? Hold on, honey. Do you know anything about lower bounds on n here? Because you have this 1 over gamma as a 4 dependence. Do you think that's tight, or do you have evidence either way?
Yeah, the only the only example that we've both worked through very carefully is this noisy 2 XOR that is by not just Wei and Mom, but also Liu and Li. So for that case, they in their paper worked it out quite in detail. So for the NTK, the lower bound is our SGD upper bound. But if you leave the NTK and you are actually learning over just shallow networks, then the sample complexity is much better. It depends on D and not D squared. So that's a specific case from the literature that's been worked out quite well. In terms of a general lower bound or just more constructions, I don't think anybody has a good guess. A lot of the papers in the beyond NTK regime, for instance, they use kinds of polynomial problems as well.
Thanks for this talk. I think I've seen a version of it before, but it's great to see it a second time.
Okay, thanks for coming a second time. All right, well, it's 1:30. I guess we can wrap up. Thanks everyone for coming.